all of the presenters in this session to submit their presentation in the laptop here in front. Morning food is already here. Dr. Vasant Adhikari, please submit your presentation. Shrudan Vikas Maharjan, yeah, please copy your presentation in the laptop in the front. Then Jaden Mo Tamak. Jaden Mo Tamak, please submit your presentation here. Subhas Dawadi, please copy your presentation in the laptop here in the front. Jarendra Kesi, already copied, right? Subhas Dawadi. Okay. Jarendra Kesi. Okay, he's coming up. So let me introduce our chairperson, Professor Dr. Dinesh Pathak, head of the department, Central Department of Geology, chairing the session. Then we have co-chairperson Dr. Suchita Shrestha from Department of Mines and Geology, and we have Sharmila Paudel from NCET as a rapporteur. So let's start the session, and I want to call Monique Ford in the beginning. This is generally the session after the lunch is sleepy. I hope you don't sleep with the presentation from Monique Ford. Thank you.
Kathmandu Nepal event of August 15, 2023, Bhutan district, Nepal, triggers sediment cascades, degrading infrastructure, how to manage the situation, and with Monique there are to go other options, and I request her to complete within 40 minutes, including the questionnaire.
I will present you some data about the Kathmandu Nepal which occurred in August 2023, and so I will like to show you the triggers, sediment cascade, and of course impacts on the Kathmandu city, and how to manage the risk equation. So most of you know where is Kathmandu. It's a small village, I could say, but it's located north of the Annapurna, and it's a really important site at the junction between the Jonkola and the Kaligandaki. And as you know, also it's a stopover place on the way to Mutilat. And so it's also just a node to the urban storm, because it's now in relation with the Kaligandaki corridor, part of the DRI project. The flood duration was very short, 2 hours, and there were hopefully no casualties, but a lot of damage. 5 buildings washed away, these 10 buildings badly affected, etc. And the bridge and cattle and trees and vehicles were washed away. As you can see in the little white circle, that's I'm sorry, it's actually, no, I wanted to show you at the junction. You see the Kaligandaki River on the cross, and so the cord extended widely because of the transport of much sediments, and there was a formation of a temporary lake which lasted 2-3 days according to the locals. And also, sorry, I forget, in the circle, this is a Kaligandaki bridge which was washed away as well. So my outline will be first, I will insist on the triggering of the flood and how it propagated and the impacts in the Kathmandu city and on building, etc. And I will insist on the change in which section of the Jonkola. That's an important point. And I will suggest some improvements. Should we relocate people in safer places? And I will mention the functional space concept. I'm not sure all of you know about that. And of course I will. Okay, just one image that's from Washington, my Republican. Just a photo to show you the disaster in the middle of the city. So So, Kagbeni is located on the rain shadow side of the river, of the Himalayas. And when we say rain shadow, it means usually there is very few rainfall and no more than 30, 50 millimeters per year, according to the data. And that's why we can consider it as a very uncommon debris-laden flow generated by two potential triggers, and the rainfall, I will insist on that, and also landslide in the upper Jongola. So about the rainfall, as you can say, as we can say, in the past, precipitation were mostly snowfall and dry, I would say cold, dry snowfalls. And now rainfall become more and more frequent in the area, according to the locals. The problem is we have only the data from the Johnson station, which show you annual rainfall, you know, the first upper diagram, and you see that there is an increase in the recent years, and you have the August month's rainfall also from the Johnson station, and you see that 2023 was exceptional. Appear as exceptional. Will it be exceptional in the future? We don't know. There was a station in Muktinat, but it was broken after 3 years and no reparation. So that's a real problem. And that's why we try to see through satellite images whether there will be another opportunity to see what happened with the rainfall. And we use the SHIRP, the rainfall estimate from rain gauge and satellite observation, the SHIRP, and this appeared in the blue lines here. And you see that the flood, when the flood happened, there is a high blue line here showing that, yes, something happened even in the upper part of the Jongola catchment, not only in Johnson. There are significant rainfall events in July and early August, okay? So rainfall should be considered as a potential trigger, not only for the flood itself, but also for triggering landslide, and I will see why. And the timing of landslide remains unclear, we will see that. And there are still uncertainty on this SHIRP system, but general rainfall pattern has been confirmed by the local people. So the second trigger is a landslide in the upper Kalkola catchment. For those who knows, just below Muktinat and Jakot, there are gorges which are in limestones, and in the upper part you see the red rectangle. We have again soft sediments, shale sediments, and so we have identified two possible sites, site 1 and site 2A and B, and thanks to so you see the narrow gorge which are downstream of these sites, and that's very important because probably it plays the role of a bottleneck and so increase the pressure. So then we studied to know whether they were really landslide. We studied with a Sentinel synthetic aperture radar and using the coherence analysis. And the low coherence means you can detect the location and the timing of the rapid landslides. And as we could see, and mostly Cathy Burrows, they are very, more likely that the upper eastern landslide, site 2A, was the most important one which failed. And then, we considered that there were two steps event. First, before the event, some days before the event, the first rainfall may have triggered landslide and blocked the Joncola. And a new rainfall event then helped the bursting out of the landslide and created the flood. And because of the bottleneck effect, many water accumulate upstream and then downstream, it spread over the valley. And that's why we had a so important event. And this could be considered as rather exceptional because we have a combination of two things. So if we go now just downstream the gorge, you see the gorge on the upper left, you see all what is gray, it's the result of the flood. And so there was a series of cascading impact, and so mostly we have the entire valley floor which was flooded at least 5 meters high, and so some new terraces have been created. I say new terraces because after the flood the river started cutting through again, okay? But sometimes they were former terraces and they were plastered by new sediments, which is the case on the right. So then if we go slowly downstream, here on the left we're at the junction between the Tonga Geocola or the Cola and the Torung Pass Cola, and we see that it's only, there is nothing happen in the Torung Cola, but only on the Cola. And so further downstream, we see that the flood reactivated landslide, and especially all the more because we have spitty shales, they are easily erodible, and as you can see here on this photo. And this is very important because it provides additional debris, muddy flow, it increases the density of the flow, and then making it even more disastrous. So, slightly downstream again, you see in the rectangle R, the tilted bridge linking Jagot and Jong, which has to be rebuilt by one of the co-authors, Narayan Gurung, working for Kaduri. And you see that slightly below, downstream the bridge, we have again some plaster on the former terraces, a new deposit forming now terraces because it has been cut again after the flood. And so the propagation of the flood, you see we are upstream and progressively going downstream. You can guess the Kaligandaki and you see the Kagbeni. And what is important, you see again this color, the gray color, which means that it gives you the high level reached by the flood, the muddy flood, and in the meanders, it's splashing higher, and so more damages. Okay, and then considering both the width of the channel of the river, the average thickness of the deposits that we observe, and the length of the river from the upstream landslide down to Kagbeni, we could calculate the volume, the landslide input, the initial landslide input, and then the channel transport. You see the number of cubic meters, quite a lot. And then after the flood, as I told you before, the remnant of the flood start cutting through to re-establish the former level. So it represents about 1/3 of the initial sediments. Now let's see the impacts of the flood at Kagbeni. And there are two sites which are important. In the village, of course, and at the bridge deck of the road leading to Upper Mustang. And we will see that it has been played an important role. So first, I mentioned that in the beginning, the impact of the flood at the junction with the Kaligandaki. You see it's the remnant of the lake, but now it's not blocked totally. And maybe you heard about that in newspaper. Of course, the Hindu temple was washed away. And what is important, most trees which were along the river banks were uprooted and that provided, they reinforced the lake, the dam of the lake. But let's see now what happened in Kathmandu. You see the impact. You have two another slide image, satellite image, before and after the flood. You can see across Kathmandu all the material here. You see here, all is green. And so you can see that all the house damage in red, in orange, those buildings very affected. All the bridges were destroyed and many things. There were no casualties, and so that's very important because even there was not an early warning system. Actually, the local villager of Jong, of Jalkot, etc., they called their relative saying, "Be careful, there is a big flood going down." And so they were all safe, they went out. And they were helped by their relative as well. But I want to insist about that. If you look at the different sections, if you look at you see the section number 11, 10, etc. And you see, look, this gives you the section of the Kola here. And you see that at 11 number, it's 54 meters. The bridge itself was only 25 meter width, and in the village itself it's less than 10, even lower. So, reduced channel with downstream despite increasing discharge. So that's really which created the most problems. So the flow of the river was blocked by the narrow bridge and passed over around, and so could flood in some little street in the village, and mostly on the right bank. And additional jams were created by the trees which were washed away. Then I want to insist about the bridge. The concrete deck was displaced, and with a zigzag trajectory, he's responsible for the all you see in gray. It's everything which has been flooded. Okay, and it destroyed a lot of buildings. Now, just a few examples to make you memorizing that. You see, some photos are taken from the newspaper, some others were taken by Narayan Guru, who visited the place just after the flood. And then I want to insist, you see on the left, you have an upstream view of a place that's very close to the entrance of the Kathmandu village. And you see that the flood has reached the second floor of the building. No more Jonkola channel. It's all sifted, all buried by debris. And you can see the debris flow away with large boulders as well. I tell you, because of the high density, larger boulders can be carried out. And from the same spot looking downstream, you see that. And you see the blue, the trajectory. No, we haven't done that yet, But apparently, nothing special happened in 1924.
Less compared to number 3.
Sorry?
For this very nice informative presentation. My name is Durga Pavel. I'm a faculty member at the University of Louisiana in the USA. I'm a professor of environmental science program. And my question for you is that we do fraud modeling in flatland or in other areas in the riverside. Do you see any prospects of developing some fraud forecast models for the high altitude flooding events like this, which is very highly debris flow? And more of the landslides also there. So do you see or do you think any chances or any constraints or opportunity, any thoughts with regards to developing some flood models for this high altitude flooding event? Thank you.
I have to say that we try to reach that place where the potential landslides, we wanted, but it's a very inaccessible area, very dangerous, and the locals discourage us to go there. So that's why we did prefer using satellite images. But I think that you have to consider mostly the nature of the bedrock. And those sites I have mentioned are developed in the shades, shade. And we can see the landform, with some sliding, some landslide already. Okay, so, but I would say it's difficult to predict in advance, because there are many sites, and which one depends also on the rainfall, sometimes you have stormy, and it will be more in one site and a little more spread nearby. So it's really difficult.
Well, thank you very much, Dr. Ford, for your presentation on the geohazard in the northern part in the high altitude. And I would like to request for the next special paper that the understanding of cascading hazard for risk informed decision making in the Asian highland by Dr.
But the process of understanding is still there. So today I'll just drive you to the understanding of cascading hazards in the Hindu Kush Himalayan region for decision-making process. As you can see, this is the drone footage or drone image that taken in Gorkha district, where you can see the debris flow, suspended bridge, interaction with the riverbed. So we have to build our infrastructures, which should be resilient in the context of changing world. So if you just look this image carefully, you can see this gray color debris, which used to be a glacier. So glaciers are melting. So if you look at the major drivers for geohazard, there's a strong monsoon and very long dry winter. We haven't done any study in the Nepal Himalaya, but for our study in Sichuan province in China, in 40 years, but we found that when you have a long dry winter and then the excessive rainfall, then it creates more debris flow. So that's why this is one. Another one is the seismic destabilization. Climate extremes are there. Climate change is not that a problem, but extremes are problems in the Himalayas. Please be careful on that. The permafrost melting is very challenging, and we didn't know the best understanding about permafrost melting in the Himalayas. There are some few studies in Alps and Andes, but still in the Himalayas we didn't have that information. Forest fire, which is increasing, and then, of course, the anthropogenic activities, what we call desert terrorism in this country. So let's look some of the example. This is very good example in Pakistan, in Hunza Valley, where we had a glacial lake outburst spot, and it destroyed one of the very important bridges in Karakoram Highway, which is called China-Pakistan Economic Road Corridor. This is Chamoli in India that happened, rock slide, and then destroyed the hydropower downstream. And this is the Seti flood in 2012 in broad daylight. We lost nearly 70 people. Melanchi, as we have already heard in many seminars, you can see before and after image. This is Botikosi. The glacial lake burst was happening in 2016. And you see the devastation in every spot. And this is the Thame. I'll not talk more because my colleague Sudan will talk more on that later on. And then this is the flood in Tista River in Sikkim after the Lunak Lake outburst flood. And there is another very beautiful example from Bhutan. There is called Bhavani Jora bridge, which were completely destroyed by debris flow. So these are some examples of many where you can see the different these geohazard events are happening. Why? Because the climate change. If you should see this Rongbuk glacier before and after in 1921 and 2008, couldn't see any more the glacier there. In Nepal side, in Inja Glacier, here you can see there was a glacier in 50s, and now in 2007, and now the glacial lake is already there. So the acceleration of glacial formation process is there in the Himalayas, which is really threat for us, for the people's livelihood and infrastructure development. If you look this very interesting paper, published in 2019, you can see this most of the concentration of glacial lakes, volume-wise and size-wise, concentrates in the central part of the Himalayas where you have Nepal. And due to the change in climate, the potential lake burst is there, which is one of the example is Virendra Tal that happened in just recently. Although the moraine did not breach that much, but we had a flood later to the downstream. Here you see this Asama village, which is nearby this river, and just imagine what would be the consequences if this moraine burst. And after that, this is the report published by Isimore. Here you can clearly see that the detachment of glacier created the source and created the flood to the downstream. So not only the moraine failure, not only the increase of flood or the water volume in the glacial lake, but also the impact of glacial detachment or debris flow or landslide to that river, to that lake is really challenging for us. As I already, this photo not from Virendra Tal, this is from Thame, and you can see this the changes in the downstream when the lake was crossed to the upstream, and you can see the before and after. And so these are the very preliminary studies that we did from the satellite images. So what is important, because I already told that Sudan will highlight that later on, but what is important here to understand is that we're always talking about, okay, there are 200 potentially dangerous lakes to be crossed, or 5 or 20 in Nepal or so. But see, this very small lake was crossed, and we had the consequences. So that's why now time to think about what is the change, what is the effect of climate change in the Himalayas, even in a small volume of glacial lakes in the Himalayas. So that's why we have been doing research throughout the whole Indus Himalayan region, because the sediments are there, and we don't know what would be the consequences if the sediment just slided down or transported down by the different geological agents. So that's why our research team called sediment bomb. So the bomb are there, and we are leaving to the downstream. So that's why we have to think while developing our land use plan and other things. So see, this is the Botekosi. You can see the lake was burst. This is 2014-16, and this is the Kodari highway. And the lake was burst in 2016. I'll show you some of the studies that we have taken that published in Science in 2018. So you see, if you look at the different colors of the river bed width, and that is significantly increased in 2016 after this glacial lake flood. So in the Himalayas, it was long-hanging discussion that whether one single event can change the landscape or the continuous process or geomorphological processes change the landscape. And we found that one large single event can change the landscape significantly compared to 50 years or others time interval. And you can see, this is the before and after, the image that we overlap. You can see this negative is the erosion, and then the red color, blue is the erosion, and then the red is the deposition, which shows that the river has already shifted. So when you have a river shifting, there is a toe erosion, and then the landslides, and then the consequences to the downstream. So I will give you another example, just recently published by Satar and others. You can see this Lunak Lake flood, glacial lake outburst flood that happened in Sikkim. You see the before and after. So you see that there is a slide in that lake, and then the moraine was breached, and they have mapped all the way through from glacial lake to the downstream in many stretches. They have calculated all the volume and the destruction of the bridges, houses, agricultural areas, and others. So if you look closely, this glacial lake actually brought these two coming down. So this is the before and this is the after. So you just imagine such kind of glacial lakes are in the Himalayan region, and we are developing our hydropower to the downstream. Are we considering that? Because we are investing billions of dollars for the clean energy. Are we considering? Did we consider? If you look at the data, very less, very few hydropowers they consider such kind of potential hazardous situation for their project. And if you see, this is very interesting study, that's why I have highlighted. They have calculated from upstream to downstream in different areas about the destruction before and after. Not only that, the agricultural land, the households, the bridges, and whole systems they have mapped. And these examples clearly highlight the necessity of understanding the glacial lakes in the Himalayas. And not only the study, not only the making inventories, but the consequences. There are different scientific methods to calculate what would be the scenario if the glacial lake outburst happen. So our planners, our developers should consider that while developing different strategies for the national building. And the Belanchi, I'll go very shortly because this is Belanchi, just if you don't know where is it, for our international participant. But what is very striking over here, if you fly there, you can see this, the erosion, and you see the nick point. So when we went there, before and after, the nick point is shifting. And the important thing is that you see the deposition. This is the recent deposits. But if you go there and look closely, you can see the different sedimentary layers there in the old deposits, not in the recent deposits. If you are a sedimentologist, you can clearly see the sedimentary layers in the older deposits, which explain that the river was dammed long before. We are doing some vessel dating to understand the damming. So that similar kind of river damming are widespread in the Himalayan region. So that's why we call the segment bomb. If you go in Mursangdi, Talbagar is there. If you go in Kaligandaki, for example, in Leyte and others in upstream, there are many such kind of deposits, or even below. If you go in Karnali, there are other things, or in India and Bhutan. So we have to really think about why these things are happening and what are the processes behind it. So some of the photographs for our international participants, you are not familiar, so this is a before and after, before and after. Just recently I took the picture. And this is before and after. And this is Melanchi Bazaar now. What is important in Melanchi, you see the different processes that published by Simon, Sudan and others. They showed their different activities on that. But what is striking here is this, the cascading effect. So one hazard triggered another hazard. And this is the real challenge that we should understand for the national development and process understanding. So thanks Monique for highlighting. I went there also. I partly agree with your interpretation because when I was there, I saw that the sediment deposition there and pretty much showed that the river was dammed somewhere here and then burst. But we don't know where is the landslide progression because it was very temporarily blocked and we cannot actually detect the site. But what is very important here, you see the sound is not there, but this is the video. You can see the flood on that time, which clearly shows that the river was dammed for certain hours and then it crossed. You see?
There are 2 minutes, Dr. Rodriguez.
Okay, so if you look to downstream, you see the river level lowering, which explain also the river damming. And this is the recent flood that 2024 that happened in central Nepal. You see the different consequences in different areas. And this is the remarkable rainfall that detected in 57 years in the central Nepal, which is really, we called climate extremes. The climate attribution has already done there, and you see the different data. And some of the photographs that you can see, some of the devastation by LGRRMA calculated. So, and then we wrote a paper, what is the taking SETI, Jure, Boiseri, and Melanchi, different mode of cascade mode impact and disaster in regional, local, and national level. This is what we need to understand. I, as a geologist, I, as a geomorphologist, I, as an engineering geologist, are working in this area, starting from high Himalaya to the lowland, different geophysical systems, potential hazards, and then the impacted sectors. Because we have to build our lesson, and we should consider that process. So, the way forward, the infrastructure resilience without considering climate change is no more option in the Himalayas. The utilizing geological information is there, should be there for policy making. Thanks Moni for also highlighting, we have to establish the hydrometeorological station above 3,000 meters, because we are now relying only on the satellite images, which is not correct in the case of Himalayas. Commitment for the long-term monitoring and innovation, which we need to use the cutting-edge technologies to understand these processes. And investment in resilient infrastructures and early warning system, because we have already seen the devastation of Melanchi water supply project, which is the lifeline of Kathmandu Valley. So that's why let's work together to build this nation through the geohazard investigation.
Thank you, everybody.
Yeah, thank you for the presentation. My question is, you showed the picture of the hydro dam, that's no more. What are ways, and maybe this isn't your area, but how, we shouldn't abandon hydropower, but is there a way to set smaller dams upstream? How do you mitigate this problem and still get hydropower?
It depends on the locality.
Yeah.
Of course, the one way should be creating a small dam, obviously. But most important thing is that to understand the process and the continuous monitoring. I mean, you cannot really stabilize the glacial lake outburst flood and the impact, but you can divert. So that's why you cannot make the resilient, risk-free infrastructures. You cannot make that, but we have to minimize the risks. That's my understanding. Thank you.
I am Dinesh Pathak. My question is regarding especially the glove event, not the rainfall-related event. There are many globes occurred in last decades, last years. Did you have any information regarding the impact zone of the globe? Suppose the overall river stretch is about 100 kilometers. At the top of section there is globe happen, okay? Then after how downstream, how long it had affected that area? That is my question.
Yes, studies in Nepal for some glacial lake outburst flood. For example, Ishimon has done some simulation of the numerical simulation to the downstream. But I showed the one beautiful example by Asim Satar and others in Lunak Lake, because he has done before the Gulf also. So that's why he has written a paper in 2025 in I think it's in Nature or Science. So we have to do that, and we haven't done all the glacial lake outburst floods. What would be the consequences to the downstream? But the science is there, methodology is there, we should start that. Thank you very much.
Thank you. Now the part recording is reserved here. With internal, there are other associated question and answer. So I request you to complete within 12 minutes.
Thank you, sir, and thank you, Basanji, for. I'm from Ishimot, working in Ishimot since 2009, especially focusing on these glaciers, glacier lakes, and geohazards. So this time I'm coming up with the flood disaster, which happened in the Kathmandu village, which is very close to the Namche area, the region last year. So this is entirely work to support the government of Nepal, which request from the NDR, I think. And we joined with them with ADB team, BGC team, and NDR team to investigate what is the main cause of that crop interjection in the Kathmandu Valley last year. And and also suggest what could be the risk reduction part on that valley. So I'm with my co-author, my colleague Tenzin is here, who is from the Sulukumu Namche Bazaar. So we have a good team to investigate locally as well. So yeah, so this is the photograph from the Thame villages. When we were there, we took that photo. You can see the damage at this. So further going, if you can see the Thame village is at the northwest of the Namche Bazaar, which is in the Everest region, and exactly around on 16th of August 2024, exactly around 1:30 p.m. there was a big flood at the time of the village over here, and we immediately after we got the information, and then we started digging on what the main causes of that flood, and we identified that there is a glacier lake. Looking at the flood that you can see, we already assumed that the actual cause of that flood is the Glock, but from where, of which lake, and how it happened. So for that, we immediately went through the series of remote sensing kind of analysis on it. So this is the slide how we can show the Glock start from this pipe, and then it cascades down to another lake, and then there is some cascading effect at the downstream, about 3 kilometers downstream, where we call the Tango outwash plain. This is the glacier outwash plain area, and then we can see there is an opening of the valley, like a wide valley, and Thame village, impacted the Thame village. So my presentation will be more focused on these 5 points, and then if you can see this longitudinal profile versus the flood impact, flood bit of the valley, starting from the mouth of this lower glacial lake resort point. So you can clearly see that after the reaching of the lake, the massive erosion and leading to it. When it comes down, with increasing steepness of the valley, massive erosion happened. And then at the Tango area, the deposition where the glacier outwash plate was there, the deposition happened. So from this analysis, what we found is like the major disaster happened in the Thame is not only due to the glacier lake outburst flood, but due to the geomorphological and geological conditions at this process. Because after the Tango flood, the valley is narrow, pushed by the many fan deposits and the paleo-glacial deposits over there. So that followed the massive sediment and it impacted the Thame village. So going to the upstream, you can see the 5 most prominent lake at the Thame valley. So what we categorize is the first one is the bedrock dam. So that means the rock is from behind the bedrock. It's very rigid and there is no chance of it. So while saying this, in the glacier terrain, bedrock dam, but still there is some thin layer of the moraine over the bed dam. So that part is there. Whereas others you can see this is the moraine dam, this is the in moraine dam which was this time this is the lateral moraine, we call it, blocked by two moraine, and this is also the in moraine, and this is, you can see there is no lake. Mostly frozen, but there is a lake, and then it's formed on the glacier surface. If you see this terrain, it's all glacier, it's ice on it. So same way, we have naming the lake based on the local naming. So you can see, start from the hydrological cycle. We just lake 1, lake 2, lake 3, lake 4, and the bridge lake is 5 and 4. So and it's not so much clear. So I just want to show you that the development of lake. Mainly 3 lake, you can see the consistently showing the size, but the main lake is breeds out from upper part. Before 2008, there was no lake. So with melting of glacier, it forms a lake, and then slowly it increases. But and lake one is, you can see, is forming and draining seasonally and over the year, and it's also large. So and this is the remote sensing analysis that we did immediately after the event, which we access. So we tried to find out what the main cause of it, and what we found is two lakes. One lake is breached out. We are very much clear, the lower one, because it is impacted by the upper lake. And we know that, as you say, upper lake is bedrock dam. We thought that there is no chance of breaching another, only the overspill of lake water. But what the cause of it? So we tried to find out by using the remote sensing, but it is not possible due to the terrain condition, and satellite image also cannot capture it. We also use the INSAR data and others, but orientation of the slope and the lake area of the valley, we could not identify the exact causes, what the main cause of the lake spillover. So there is a big chance of ice avalanches and rock avalanches that we assumed that time. And then later on, we have been invited by the NDRRA to support them to identify what the main cause of it. So we visited with my colleague Tenji, and so these are the activities that we have conducted: UAV survey, DGPS survey of the profiling of the moraine and others. During that time, we are able to do the UAV survey at the Thami village, but due to the wind and terrain condition, we are not able to do the UAV survey over the lake area. So the finding is like this rock avalanches happen over there. It's about 200 meter height, and it collapses into the upper lake, and the wave created from this rock avalanches, it created a flood over the downstream. So these are analyzed stuff. And then we also try to identify whether there is an ice avalanche flow, but we could not find any sign of ice avalanches or snow avalanches or the debris flow from other side. But still, there is a high chances of expanding this lake. You can see the ice over there, about 300 meters. It is still has chance to grow at the backside of the glacier. And then there is a high chance of debris flow, ice avalanches, rockfall, rock avalanches, and so on. So this lake is still in risk, say in terms of like it will not reach totally, but like it will overspill of water. That can also create a flood in the ocean. The next one, this is the measurement that we have taken. We can clearly see the lake level of the peak level and the breeze width. So this is about like around 4.6 meter height of it. You know, after the bridge, you can see clearly the bedrock of that location. So there is no chance of deep breaching of it, only the spillover of water. If it's impacted from other like rock avalanche, ice avalanches, or so. Same with the lower lake, you can see the breach part over here. The lake is lake size very significantly. So you can see the breach width and breach height is almost 51 meter of breach width with more than 21 meter of the breach height. So significant amount of water release, which we approximately can calculate based on our measurement and remote sensing data. 300 million liter of water release from this lake. And then while we come to downstream, about 3 kilometers downstream from this lake, you can see this is the outwash plain of the glacier, the terrain, and then this is the glacier moraine of the other side. So due to that, there is a significant erosion on the glacier side. But while it comes down, all the energy brought from that glacier lake flood dissipated. I mean, the energy came down, and the sediment deposit overflowed here. And you can see almost 2 meters of fine sediment deposit at this flat land, whereas the coarser sediment deposit at the upper side. Almost all the coarser sediment was deposited incident and the finally. So this indicates that there is some temporary blockage at this point, and you can see this now where it's again releasing, which is around like 3 meter high of this bridge area. So after this, there is a massive erosion because the river valley is so narrow, pressed by the side by the fan deposit, sequence of fan deposit over there, and on the left side there is moraine valley moraine deposit over there. So significant amount of sediment doesn't happen there. So this is just like about a kilometer away from the Thame Beaches. And you can see the sediment it start in deposition after it. So this is Thame village of the three men. So you can see the Thame village located at the glacial limestone deposit. That means in past this area, particularly this area is a glacial lake. So it was released some time back. So, but the settlement happened, agricultural land, all the infrastructure developed on this glacier limestone deposit. And in the upper side, these are mostly the glacial sediment deposit. It forms like a fan shape. The river is braided, and you can see the interesting part. The one seasonal braided channel is going through the middle of the village settlement. And you can see that's the hydropower, which is a lifeline for the Namche area, the most touristic place of Nepal. So and this part are in moraine, in moraine part. You can see this landslide. This landslide happens due to this previous block, the Dikcho outburst, which happened 40 years back. And this is after the flood. This is the UAV flight data. So you can see how the sediment deposition pattern and impacting the villages. So after releasing from this apex point, the single channel, the multi-thread channel, so you can see it is spreading like a fan, depositing more sediment upper part, whereas the one channel flowing at the middle of the sediment which impacted the village scenery. And when it comes down, it forms a single channel and incising the river. So almost like the deposition is about, or here is about like 2 to 5 meter thick sediment deposit at the main channel. And then here the incision is about 5 to 12 meter of incision happened at mostly at the glacial limestone deposit. So
would you like to complete within next 1 minute?
Sure. So this is the present condition, and we have suggested some channel hygiene, diverting the channel to prevent the village from the most next disaster happen. And you can see the tension crack is due at the glacial limestone deposit, and also the landslide, which is very much impacted to the source tank of the hydropower. This is the dam area. This is the south tank over here. So the tension crack, you can see the landslide from the eastern side is extending. So the solution is like we need to protect from the surface flow into the tension crack and also the channelizing river bank. And this is the impact the intake of that hydropower. So you can see the intake was up. And there's the future risks. As I said, this lake is still in danger. It will breach, but like the overflow from this can impact this lake, and also some overflow is there. And one is another two lake is like this is more stagnant lake, so because this lake is had more and the freeboard is so high, so this is little low lakes, whereas this is at the water is big because the landslide erosion at the dam area is going, and there is a glacier flake, but it's quite far away, and there is no chance of anything back from that. So we categorize this as a moderate itself. But the main concern part is this one. You can see the ices at the moraine, and this lake is formed on the glacier surface. This is at the high rate, so which needs a more detailed kind of geophysical study. Next, so in February, so this is due to not only the growth, but the cascading impact by the geological and geomorphological features along the valley. And the best part is like we have prepared this hazard map, which clearly shows that what kind of integration of there and what will be the things need to be considered for proper planning of this time and varies of it. So therefore using the Linus Planck development and others, hazard map is very important. So this map we have developed of it and going to submit this to the India and May. So same way, like finally, I would say like for early warning and others, structural as well as non-structural is very much important in this region because like when it comes. Yeah, sure. Just this is last slide, sir. So the main part is non-structural is the main part because like community-based kind of preparedness is very much important. And for the long-term understanding, hydrometeorological monitoring stations should be installed for better early warning. And another recommendation or the way forward is like we also identified the glacier lake over the whole Nepal and identified potential dense glacier lake. Although we are saying those lakes are very much large, but the small lakes are branching more frequently. So you can see the lake, more than 80% of lake are very much smaller lake. So this need to be kind of identify the critical areas and keep on monitoring on those things. With this, I acknowledge these institutions who give permission and support to us.
Well, thank you very much. So regarding the time constraint, I would like to request for only one question.
Identify or guess potential predictors of glacial lake outburst flooding. Thank you.
Yes, exactly. I have been working on this identifying monitoring glacial lake and also identifying the potential glacial lake. In 2020, we have released a report covering Nepal, including China, the three main basin which fed in through the China and flow through the Nepal and then India. So we have identified 47 potential dense glacial lake. While saying this, that report we have published to understand what could be the most prominent kind of impact happening downstream, so that the government should take initiative for identify the potential dense glacial lake and use those data for the mitigation purpose. But while saying this, we have also worked on like considering the basin-wise prospect, small catchment-wise prospect, considering even the very smaller glacial lake that we can map from the remote sensing tools, and then we have also categorized those individual catchment, or especially we did that for the Gandaki basin. So we are and also the Karnali side area. So that kind of things we can do from remote sensing. But while saying this, also we need to understand more on geological and geophysical, because while the lake breathes out, it will not only because of the glacial increase, but it can also intensify the impact to the downstream due to the geomorphological and geological condition. The best example shown by Basanji about this 2016 drought in China, which impacted the potential.
Jack, even during the other time after the session, and thank you for your presentation. The first presentation is on tracking thought events including glacial lake outburst flood in a warming climate using seismology. And the team is on the Ziren Mohtaman et al. I request you to complete your presentation within 12 minutes.
I'm Ziren Mohtaman, a previous undergraduate student studying at the University of Texas at El Paso, in the United States. I'm very excited to present our research on tracking flood events using seismology, particularly glacial lake outburst floods, in short GLOS. This research is a collaboration between the University of Texas at El Paso and the Department of Geology and Mines in Bhutan and the National Center for Hydrology and Meteorology in Bhutan as well. Our goal is understand and improve to understand and monitor GLOFs, which could be a significant hazard in vegetated regions, particularly in Bhutan. Before diving into details, I would like to define what GLOF is and what triggers them. And then I'll provide an overview of the regional risks, our research objectives, and the methods that we are using, including seismic datations. Finally, I'll discuss our field deployment plans and the broader implications of our study. Let's start by understanding what GLOF is and what causes them. So a glacial lake outburst flood occurs in a natural dam, which is usually composed of ice or moraine, suddenly fails, releasing a massive and often destructive flood to the downstream. These floods can happen within minutes to hours, which leaves such a little time for the communities to respond. There are three primary triggers of GLOF. The first one is slope failures, such as landslide or rock falls, which displace water in a glacial lake and causes overtopping. The second one is glacial melting, where rising temperatures weaken ice dams and causes glaciers to retreat, increasing the water in the glacial lakes. Thirdly, the third trigger is the permafrost degradation, where rising temperature destabilizes once frozen ground, increasing the likelihood of dam failure. With the rapid pace of climate change, the risks of GLOF is becoming more frequent worldwide. GLOFs pose a serious threat to around 90 million people across 30 countries, especially in the high mountain regions, which includes Bhutan, Nepal, and northern India. These communities often live near the glacial lakes, which makes them very highly vulnerable. Bhutan's Lunana region is especially at risk due to the rapid expansion of glacial lakes. Without proper monitoring and early warning systems, these floods could cause very catastrophic consequences to the downstream communities. Now let's take a closer look at the specific lakes in Bhutan that are at the most of triggering GLOFs. Bhutan is home to several glacial lakes that pose potential risks of GLOFs. This map highlights this. So this map highlights some of the most critical lakes, particularly those located in the high mountain regions of Lunana. The blue dots represent the glacial lakes, and the rivers and the administrative boundaries are also marked over there. And on the left, you can see the specific lakes in Bhutan, which includes Bejunso. Did you see this? Which includes Bejunso, which includes Lugeto, which includes Rastranso, and the Thotomi Glacier, that have experienced significant changes over time due to glacial retreat and associated significant hazards. The box areas in the images highlight threats such as calming icebergs, landslides, and unstable moraines, all of which could trigger GLOFs. Understanding these risks is crucial for disaster management and mitigation efforts. Monitoring these lakes through remote sensing and field observations helps identify early warning signs and implement preventive measures. To address these risks, our research focuses on key objectives that will enhance our ability to predict and mitigate GLOFs. So our research focuses on 4 key objectives. The first one is characterizing the structure of the Lunana Glacier and the nearby moraines to understand how they evolve. Secondly, monitoring glacial hydrology using seismology and radar to detect changes in water flow and ice dynamics. Thirdly, studying high mountain geomorphological processes, which includes landslides, erosions, and sediment seismic transport, which contributes to GLOFs. Lastly, evaluating the potential of seismology to detect changes in river flow in GLOF-prone areas, which could provide early warning signs. By achieving these objectives, we hope to enhance hazard assessment and preparedness. To support this effort, we have utilized advanced tools like QGIS to create 3D models of the glaciers that help us analyze the surroundings around these glacial lakes. To better visualize and analyze the changing landscape of Bhutan's glacier, we have used QGIS to create a 3D model of the Kathmandu Glacier. Kathmandu Glacier is an expanding lake, which is a growing concern in Bhutan for now. As seen in previous cases, like the 1994 Geological flood, which caused catastrophic damages to the people and the community downstreams. This model allows us to assess changes over time and identify high-risk areas. Bhutan currently has both manual and automatic monitoring systems to monitor the glacial lakes. This includes on-site observations and water level sensors. However, seismic methods offer a promising new approach to enhance hazard detections. By analyzing ground vibrations caused by the water movement, we can detect changes in the river flow patterns, which may indicate an impending flood. A recent GLOF event from the Kathmandu Glacier further highlights the urgency of monitoring these glacial lakes. This slide focuses on a recent glacial outburst flood from the Kathmandu Glacier, a known high-risk area. The diagram on the left, it illustrates the structure of the glacier and the subsidiary lakes, and also shows how the glacier is interconnected with the subsidiary lakes as well. And on the right side, you can see the images from NCHM, which shows before and after views of the affected area. The flood event led to significant landscape changes, as you can see in the picture. And the flood event led to significant landscape changes, with water from the main lake reaching its natural moraine barriers, affecting downstream regions. The red labeled areas indicate key features, including the source of the flood and impacted lakes. To improve monitoring, we are leveraging seismic stations across Bhutan. Bhutan has several seismic stations distributed across the country, as shown in the QGIS generated map. These stations, marked in red color, monitor seismic activity across Bhutan, which is collected by the Department of Geology and Mines of Bhutan, which plays a crucial role in earthquake detection, hazard assessment, and geophysical research, contributing to better understanding of seismic risks in the area. By
2 minutes, Ms. Kamal.
By integrating seismic data with hydrological models, we can better understand and predict GLOFs. Now let's examine a specific case of seismic detection in Bhutan, recorded at the Wandi station in 2017. In 2017, the Wandi seismic station recorded a significant event, possibly linked to a landslide or a rockfall event. The waveform shows strong ground motion. The top one is showing the north-south movement, and the bottom one is showing the east-west movement. These signals indicate a major geological event which could be related to flooding or slope failure. By analyzing seismic signals like this, we can better understand how GLOFs manifest in seismic data, which brings to our next slide on seismic spectrograms. To further analyze this event, we examined seismic spectrograms. The left one is the north-south movement, and the right side is the east-west movement. And on the horizontal axis, you can see, on the vertical axis is the frequency, and the horizontal axis is the time, and the color intensity is the is the intensity. It represents the seismic signal amplitude, and understanding these signals appear in the seismic data allows us to refine our methods for future geo apps, which leads to our upcoming field deployment. In March 2025, we will be conducting a field trip to Bhutan to install seismic stations near Punakha and Puchu River. These stations will continuously detect record the seismic activity using Raspberry Shake 3D sensors. The collected data then will be telemetered and processed both in Bhutan and then at UTEP. Our goal is to connect seismic signals to sediment transport and river level data from the Bhutan NCHL. Ultimately, our findings will be communicated to the local communities to enhance real-time GLF monitoring and improve hazard assessment. Beyond Bhutan, this research has global significance. Our work contributes to Sustainable Development Goal 11, which focuses on making communities more resilient to disasters. Additionally, the methods we are developing could be applied to other glaciated regions to improve flood risk management worldwide. By integrating seismic monitoring with hydrological data, we can enhance early warning systems in other vulnerable mountain countries. This research would not be possible without the support of our institutions and collaborators, whom I would like to thank in the next slide. This work would not have been possible without the support of the University of Texas at El Paso, the Department of Geology and Mines, and the National Science Foundation. We also thank our field teams, technical staffs, and mentors who have guided us throughout this project. With this, I conclude my presentation. I will be happy to take any questions.
My question is, if you are installing a Raspberry Pi for glove Kaliwani in the higher altitude, okay? So for the Raspberry Pi, you need to connect with the internet in the power supply. Do you have that kind of good internet connection in the high altitude in Bhutan?
No, we are not actually going all the way up to the mountain. For now, we are planning to deploy in the lower valleys as of now. I think the weather can be pretty harsh in the upper regions for now. So for the first time, we are just gonna go in the valleys for now.
Okay, thank you. My second question is, since the glove can be very locally, so what is the station density? I mean, how many stations are you going to install in which distance? What is the number of stations you are trying to install?
For now, I think we are going to install like around 5 to 6 stations.
Okay, it is 3 component, yeah?
Sorry?
It is 3 component. Raspberry Pi 3 component.
Yes.
Thank you.
Next presentation is on the topic of assessment of the 2021 delivery flow and all related loss and damage in Melanchi watershed of Central Nepal. The presenter is Suhas Dawari, and the other one to others are also pushing. Now it's time for you, and you also have.
Central Political Campus and 2021 debris flow and flood related loss and damage in Melanchi watershed of Central Nepal. And I am PhD scholar from Central Department of Environmental Science, and my supervisor is Professor Dr. Adhikari, co-supervisor Professor Dr. Meghraj Vidal. My presentation is basically related with introduction, objective, materials and method, causes and consequence, result and discussion, conclusion and recommendations. Background. As you already know that flood and landslides are the landslide basically is downward and outward movement from the slope forming materials. Either it is from pore water pressure and animal movement and many other causes cause landslide. And basically background is flood and landslide are frequent natural disasters in Nepal which occurs in monsoon time every year. And this is the DEM digital elevation model of Melanchi area. And we can see the conjugal point over there. Conjugal point is between Melanchi Bazar is the conjugal point of Indravati and Melanchi river. And this is the conjugal point where the two sections of the rivers are joined. And Department of Hydrology and Meteorology data shows heavy rainfall in 2021 monsoon period relatively to the previous years. rainfall has caused flood and landslide all over the country, and all debris flow is moving mass of the loose mass sand, soil, rock, water, and travel downslope under the influence of the gravity. That we all know that. And yeah, this is while talking about the devastating phenomena like flood, there is an intake and there is a erosional section, transportation section, sedimentation section, many sections over there. So basically, Bhemangthang area is the upper area from just below from the bluff originating area. Bhemangthang area before flood and Bhemangthang area after flood. We can see over here that this much sediment has been accumulated over there after the flood in 2021. So change pattern of the Melamchi river after flooding in Bhemangthang region. Yeah. My basically this is part of my PhD research work, and this only includes to study the causes and consequences of the Melamchi flood, to study impact of Melamchi debris flow, and assessment of the loss and damage through particle size. This research only includes these three objectives. So this is the materials and method where I can survey quantitative approaches as well as qualitative approaches. You can see over here that physical structure, public infrastructure, schools and hospitals, dams, these all are the quantitative approaches. How much the sediment, accumulation of the sediment has damaged the infrastructure. These all categorized in quantitative approach, and another is qualitative approach. In qualitative approach, mental and physical illness, disabled injuries that has been surveyed during the field visit. And study is based on the purposive sampling method, which is the judgmental sampling method, which is conducted by studying the characteristics of the study area. So this is judgmental sampling, and I have two main approaches have been conducted in this research. One is 32 WPT were taken as observation site and samples were collected, and this is the methodology that I applied. Source is Adhikari ETL 2025, and another one is questionnaire survey. I have conducted questionnaire survey in Melamchi and Helambu area, and questionnaire survey, focal group discussion, key informants interview, and direct observation and case analysis as well. I have conducted all this for this research, this part of my research. So Android mobile also used in the field, SRTM, DEM, digital elevation model. I also studied voluntary geographic information system. These all methods have been applied during the materials and methods proposals. And as we already see in the previous figure, the green dot in the map is where I can take the soil sample I have taken from that point, and this is 32 sampling point has been done. So study area of Melamchi river indicating, but I include over here only the 20 sampling plots, different sampling plots. And Melamchi flood, devastating flood was originated from snow cover area and downstream glacier lake drainage, Bhemangthang area, Melamchi, and this is the alignment of the devastating flood from upstream to downstream. This is the alignment up to Dolaga. And for this part of my research, we have only taken the sample from downstream from the Melamchi Hedox area. Because of heavy rainfall, we can't move ahead when we was in the field. Only from Melamchi Hedox area to downstream to Dolaga. So one of the tributary of Indravati river is Melamchi river, which originates from Jubal Himal at an elevation of 575 meter. And conjugal point of Melamchi and Indravati river is Melamchi Bazar. Yeah, we can also see in the topographic map as well. So this is the Bhemangthang area. Huge debris collected from Melamchi and Pemnam. One river that we can see over there. That one is the Melamchi river and one is the Pemnam river. And both of the river has carried out the sediment, and this much sediment has been occurred in the area. So initially huge debris collected from Melamchi and Pemnam, and steep slope converted into the plain surface. That means there is initially the steep slopes, but after the flood, because of the collection of the debris, too much debris, then the converted into plain surface. We can see over there. And this is major affected areas of Melamji Rural Municipality and Helambu Rural Municipality and Melamji Municipality. We have only conducted 2 municipalities, Melamji and Helambu municipalities. And the green dot over there is MR1, MR2, the most affected area by the flood. The most affected area by the flood. And disaster area along Melamji River corridor, that is the alignment. And we have only taken major affected areas. Study includes only from the Timbu to Melamji Bazar area. Because of different kinds of constraint, we just limited our study over Timbu to Melamji Bazar. And sampling was conducted in the major affected area of Timbu, Halde, Kiu, Chanote, Galtum, Taramarang and Melamji Bazar, and categorized into upper and middle section, Timbu to Galtum, and lower section Taramarang to Melamji Bazar. We have categorized it into upper, middle and lower section, categorized into 3 sections and surveyed in it. So after the survey, we can find that 56% people have said that lost agricultural land, and 25% non-agricultural income sources, and 11% lost employment opportunity, and 5% lost other income sources. After the survey, we can find over that. And survey is carried out by not haphazardly. Survey is carried out by the formula Arkan and Golden 1963, and also we can apply Ahmad 1970 formula. Sample size was determined by that formula. And this is Google Earth image, one of the map over there. Major sediment loss area after field visit. After the conclusion of the field visit, we can find that Melamji and Nakote to Timbu area is the narrow section river section area where there is a more kind of erosion has been happened. And Timbu, Taramarang and Melamji Bazar is the lower area where sedimentation has been happened. We can see over in the figure. And also we can see that inverse grading also we can see in the alignment.
You have 2 minutes.
And causes and consequences. Basically, causes and consequences is one of the cause is massive and continuous rainfall in Melamji watershed, but primarily caused behind the flood, because it is a cascading type of flood. Cascading means the heavy amount of the flood, huge amount of the flood in the same time, at the same time. And the rainfall trigger landslide upstream result to Melamji watershed, landslide for damming in upstream of the watershed. The result flow was not flow, etc. So causes losses and damage to the building. This is the figures that 2 or 3 states of the building has been collapsed into the debris. So we can see over here, and houses collapsed under debris. Houses damaged in the Melamji river side. We can see over here. And consequences, losses and damage to the infrastructure, electric poles, that is bridges, Ambakhan Road, washout bridge, and damaged Melamji Hedox area. This is damage to infrastructure. And this is consequences, losses and damage. Total houses swept due to the flood 242, and houses vulnerable from flood 1 to 3, and the source is Melamji municipality and our people. And domestic animal house damage 50, public infrastructure damage 41, and total 436 million in the Melamji and $62 million in the Helambu area. This much of damage has been occurred in that area. So this is the particle size analysis. As I already told that 32 samples have been collected, and this is the first sample. We can only see that gravel 41.42%, sand 57.65%, and silt and clay 0.93% in the initial part in the Hedox area. This is particle size distribution. Another particle size distribution from middle area, another from the Dolaghat area. So we can correlate all those factors. And this is Dolaghat area. This is particle size distribution. Melamji Hedox area, how the particle size is originated over there, and you see all all is here, landslide all is here. Particle size distribution in the Golaghat area, sand is 97.87%. We can see in the figure over there. There is a huge amount of the sand over there. So this is others, Melamchi Hedox area to Golaghat. This is result and discussions, and this figure also support that there is a huge amount of the rainfall in that area on that period. So Melamchi Hedox area to Golaghat, and this is another erosional section, transportation and devotional section. And this is conclusion. Still there is a high risk of the landslide in Melamchi Bazar, Charnauti Bazar, Timbo area and Kiul Nakoti settlements. Poor cutting by the Melamchi river and massive mass of devotion in Bhemantang, and these all are the conclusions. These all are the recommendations. Clearing of the debris on hydrometeorological.
Okay, thank you very much. And I request for only one query.
Comments. Since this is part of your PhD research, and PhD research generally tries to answer some scientific questions. So based on the objectives that we have set here, it seems like you are more focused on quantifying the loss and damage after that event. What questions do you try to answer through your research?
I'm trying to answer from my research that how much the sediment has damaged in the infrastructure, in other issues, infrastructure and other issues. How much the damage has been occurred. One is that, and another one is particle size analysis. That means after the flood, the huge amount of the debris has been come out from upstream to downstream, and during the period, somewhere velocity remains lower, and somewhere velocity is high. Where there is a huge velocity, huge debris has been carried out over there. So how segment size is accumulated in where? That I just want to answer in article this question. Thank you, sir, for your question.
Of the landslide and flood, and have you done any methodology for risk assessment or for the landslide? Or as you have mentioned in conclusion, there are some portions, some part are also vulnerable to flood and landslide. What type of quantification or risk assessment have you done? And another question is, you have done the sampling, and people in present days who are affected due to this natural calamities exaggerated their actual amount of risks. And how about the biasness? How do you quantify the biasness of this responding? These are my questions.
Yeah, biasness of the respondent. My work is just to survey for Lampu and Melamchi municipality. We have surveyed according to urban and Bolton formula. That means number of population is high, there has to be surveyed high. So according to that formula, there is people in that period says that actually what they have been lost during the devastating phenomena that the people has said in that period when I was surveyed. But I think and what is another question?
Okay, thank you very much. Now you can further discuss after the session on the topic of geological hazard and risk mitigation in transmission line projects across the Nepal Himalaya. Presenter is Mr. Harendra Kesi and author is Sokara.
Namaste everyone, my name is Harendra Kesi and I am working as a geologist in Rashtriya Prasari Grid Company Limited, and we construct high voltage transmission line projects. And today I just want to relate geological aspect, geohazards in transmission line development. So what are the geohazards and their risk mitigation in transmission line projects? So this is my topic for today. And my talk outline will be, I will first introduce about the geohazards in transmission line. Then I will come to transmission line development in Nepal. What is the status of transmission line development? Major geological hazards that impacts to the TL.
and methodologies for the geohazards identification, key mitigation plan and strategies, case study of ongoing projects, policy and future recommendations, and I will conclude my talk for today. In the introduction, Nepal Himalaya is nearly at the center of 2400 kilometers long Himalayan range, and it's a very dynamic region all over the world in terms of geology, in terms of seismic activities. And our Nepal Himalaya is divided into 5 major tectonic zones. They are Tarai, South Himalaya, Desert Himalaya, High Himalaya, and Tibetan Terrace zone. And our major sections are extending in the longitudinal fashion. So most of the geohazards are oriented in such way, from extending from east to west. So in the development of transmission line, we need to pass our route or the key alignment section from south to north to south. So we have to cross multiple weak sections or weak zones. So the investigation or the study of geohazards or the geology is very important there. And transmission line is itself very crucial for the evacuation of the energy. Whatever energy is produced from the hydropower section, that we need to evacuate and distribute in large distance. So transmission line is very necessary to understand that to understand the geohazards. We have to understand the hazard scenario and hazard condition and the geological pattern of that section. So talking about the transmission line development in Nepal, the history is very not a very old one, and it started from 1960s. The construction of 132 kV transmission line from Patan to Etoda. And modern electrification starts from 1970s, that expansion of transmission networks and increased transmission and interconnection with India in 1990s, expanding the grid and improving the capacity in 2010, strengthening the national grid and cross-border projects. And 2020, it's a focus on clean energy and regional cooperation and transmission line master plan. It's one of the very crucial things that's prepared by RPCL, where I work. I'm currently working there, and this is the map of transmission line master plan. And most of the transmission line big projects are near the corridors of the major rivers like Karnali, Kosi, Kaligandaki. So further, here are the major geological hazards that impacts the TL, means transmission line. So talking about the hazards, there are major hazards including landslides, land subsidence, rockfall, and earthquakes, seismic activities, slope instability, soil erosion, weathering, scouring, debris flow, and glacial lake outburst. So these are the major geological hazards, but the intensity of few geohazards are very much high and some are very less. So further talking about the geohazards, this map illustrates the transmission line section of Karnali Corridor 400 kV TR project, and this section is east-west trending, and you can see multiple of failures are located right here. And previously I mentioned that most of our hazards are extending from east to west, and we need to cross-cut that section. So we have to focus on these sections to mitigate such kind of geohazards here. So landslides and rockfall, talking about the landslides and rockfalls, it's caused by the steep slopes with geological formations, heavy monsoon, and the impact is collapse of tower or the cable damage and foundation collapse. These are the major challenges. And earthquake and seismic activity. So we know that Nepal is very dynamically very active, and it has several earthquake activities going wrong, and it has also cascading effect of ground rupture, landslide, debris, rockfalls, and liquefaction. Liquefaction is generally located in the Tarai section, and so these are the high GPA values concentrated. So we need to cross-cut these sections also. So before designing the transmission line projects, we need to consider these parts also. And talking about the globe, it is major important for the transmission line tower near the river section, because if there is globe happens and the lots of damage will be occurred in such locations. So we need to calculate before design and before constructing transmission line projects. And another is soil erosion, weathering, and debris flow. These are the major important geohazards that we need to consider before designing or before constructing transmission line. So major causes are deforestation, unplanned agriculture, road construction, and monsoon rains. Effective weakening of transmission line foundation. And prevention, we need to consider prevention such as well channelization, surface and subsurface groundwater flow, bioengineering, etc. And during the design period or during the very preliminary phase of transmission line, we need to consider about the geological and engineering geological investigation, because most of the clients or most of the parties who are involved in it, they are not very willing to invest their money to such kind of investigation. But it's in the global or our regional scenario, it's very much crucial for the good analysis and the deep investigation of the geology and engineering geological mapping. And hazard mapping, geomorphological investigation is important to understand the landforms and type of landforms. We need to understand geomorphology also, and landslide inventories, because this is the process when we analyze different kind of geodisasters in the transmission line projects. And geophysical investigation is also one of the important aspects that it indicates the vulnerability or the landslide initiation, some kind of like that. And key mitigation planning strategies. Transmission line alignment optimization by the use of remote sensing and GIS is one of the methods to optimize our TL alignment, because if there are geohazards, tremendous amount of geohazards, then we need to shift from that location to another, or we need to change our TL foundation. And site selection, geotechnical surveys are very much crucial part. Seismic resistant design, we need to redesign sometimes by taking the result of the geohazard investigation. And landslide prevention measures are very critical things. So slope stabilization and retaining walls, some kind of like that. So these are some methodologies to prevent landslides. And foundation design and mapping. Design of foundation and mapping of the foundation is very much important also. And early warning system and real-time monitoring. It helps you to understand the intensity of the landslide. If there is rockfall or the land subsidence, then real-time monitoring is installed. We need to install in devices also to understand its momentum and movement. So talking about the case studies,
okay,
there are
lots. I think we are already on some time.
Okay, I will conclude that. So overcoming challenges so there are risk mitigation and their effectiveness, and lessons are learned from the one project to the other. So we apply the outcomes from one project to the another project. So these are the case studies of Eastern Tarai region, Eastern Hilly region. These are one of the projects, and you can see the damage of foundation damage of the transmission line by this landslide, and the solution is to better channelization of the water flow here,
And these are some of other.
Okay, thank you very much.
Okay, sir.
Because we are already late and.
So this is
we are
my
consuming
conclusion.
almost our time. Thank you.
Yeah. Interdisciplinary collaboration in project execution is one of the conclusion remarks. Thank you.
So we have six presentations in technical session 4 and for the geohazards, climate change impacts, adaptation and mitigation. And first 4 lectures were presentation were basically focused to glacial lake or glacial lake or something like that, especially in the Nepal, Himalaya, Bhutan, Himalaya, and which refers to some other countries. And the last 2 presentations were focused to every flow and what damage is the energy was here, as well as the last presentation of the transmission line. Every and what aspects of the hazard and disaster mitigation and adaptation aspects should be well addressed prior to the occurrence of those disastrous events. And I thank all presenters this morning for Hospital Gary, Sudan Gas and Subhash Dawadi as well as Harendra Keshi. I think some of the presenters also learned how to make presentation and at what level you should be presented and at what level you should be on the poster presentation. And actually it's good lesson learned for presenters also. And at the same time I would like to thank my colleagues, Ms. Dr. Suchita Sexta as well as Ms. Sarmila Paudya for and conducting this session. Thank you very much for all participants.
If you need your certificate of participation and certificate of presentation, please contact in the front desk for the printed copy. Otherwise, we will provide e-copy in the email. With this notice, I would like to request the President of Nepal Geological Society